This is lecture 12 of Logika or računalništvu, Logic in Computer Science, and this week we're going to continue with the topic of Hoare logic, which was the program logic for verifying sequential programs that we were writing in this while language that is like a fragment of the common imperative programming languages that we're familiar with. We're all familiar with programs written in this form as while statements. And today we're going to finish the topic of Hoare logic. So I want to start by doing one more example using the rules we had for last week, mainly because, one thing, it's a nice example, but another one is that we did not, in our examples last week, we did not use the rule for if statements. So here's a reminder of the tableau rule for an if-then-else statement. So if we've got an if B then C1 else C2, that's the program statement, and we want to prove the assertion, the partial correctness statement that suppose phi holds in the starting state, so that's the precondition, then we want to show that after executing the program if B then C1 else C2, so the program's in black here, then the postcondition, then if it terminates the postcondition, psi holds. And well, what happens when you execute an if then else statement is that one of two branches is executed depending on whether your expression your Boolean expression evaluates to true or false. And what we know is that phi holds in the starting state, and so suppose the Boolean expression evaluates to true, then we know that phi still holds because we haven't changed the state, but also the Boolean expression is true. So in that case we'll execute C1. So as long as we know that psi follows after executing C1 in any state in which phi holds and the Boolean expression is true, and if we also know that the same thing holds for C2, that psi holds as a postcondition if we execute C2 from a starting state that satisfies phi and in which the Boolean expression that was the test for the if then else is false, then we can see then if we run the if then else statement, whether or not the Boolean expression is true or false, whatever happens, we're going to get that psi holds. So this rule is enough to give us that psi holds as a postcondition. So I want to do another example tableau proof on this little program. So we've got a while loop. While x is not equal to y, we're assuming here that x and y are integers greater than 0. While x is not equal to y, well, if x is less than y, then we subtract x from y, and otherwise we subtract y from x. And we keep on doing that until x and y become equal. And hopefully some of you will recognize this program just from what's written here. If not, you might pause the video and have a think about if you can recognize what this program does. So for those of you who have recognized it, this program is a very famous algorithm. It's Euclid's algorithm for computing the greatest common divisor of x and y. In fact, one sees this algorithm in different versions. So an alternative version is to replace the subtraction here with y modulo x, so the remainder when y is divided by x, and the same here. That's more efficient on modern computers because modulo reduces the value more quickly, but nonetheless this algorithm works too with simple subtraction. So let's use the algorithm with subtraction. For an exercise you can verify the other version of the algorithm with the modulo. So what we want to prove that this algorithm indeed calculates the greatest common divisor. So we need to find an appropriate precondition and postcondition. Well, our precondition is that x and y are both greater than 0. And our postcondition is going to be at the end, well, the values of x and y are the same at the end, so both the values, so our postcondition is going to be indeed that the values are, well, we'll see what it is. Maybe I don't put that into the postcondition. Okay, I don't. So the precondition, we're going to have x and y are greater than 0, and we want to say at the end the value of x, that's our output variable, which will be the same as the value of y, is the greatest common divisor of the original x and y. So just like last week, we're in a situation where the program changes the values of x and y. So in order to refer in the postcondition to the original values of x and y, we need to introduce some additional variables called either logical variables or auxiliary variables, or sometimes ghost variables. And so these are variables that do not appear in the program, so they're not affected by the program, and they allow us to say at the end the value of x in the state that the program results in is the greatest common divisor of the original x0 and y0. And again, we want to prove this using the tableau method. So we don't need to justify the precondition, so we mark that as a precondition, and we're going to go through and basically again work our way back from the postcondition. Right, so the statement immediately preceding the postcondition is a while statement in this case, so we need to do a reasoning by the partial while rule. So if we look at the rules from last week, well, the partial while rule is here. So we need to find our invariant, which is going to hold before we go into the while loop, will be preserved by the body of the while loop, and then is going to be true at the end. So if we go to our program, well, what's the appropriate invariant in this case? Well, it's not totally easy to think what it is. So if you want to pause the video and have a think what it is, then you can do that. Otherwise, we'll just step forwards. And so here we see the main thing that we want to show is preserved is that as the variables x and y vary during the while loop, so x and y are going to change, although those values of x and y are going to change, the greatest common divisor of x and y is always going to remain invariant. It's always going to be the same, and that's going to be the same as the greatest common divisor of x0 and y0 at the start. And we also are going to include in our variant that we never lose the property that x and y are both greater than 0. So the invariant, if we go back to the while loop, the while rule, we put the invariant before the loop, we put it at the end of the inner statement that we repeat execution of in the while loop, and then before that statement we put the invariant together with the Boolean test, and at the end of the while loop we put the invariant together with the negation of the test. So that's what we've done here. Here we have the invariant again, just as it is above. This is our eta. Here we have the invariant together with the test being true, so that's that x is not equal to y, so we've added that. And here we have the invariant together with the test being false, which is x equals y. So this is justified because this is the postcondition from a partial while loop. This is justified because this is the do precondition. We still need to justify that the body of the while loop preserves the invariant, so we need to justify that the invariant still holds at the end of the body of the while loop, and we need to justify the precondition before the while loop. So we'll start with the body of the while loop. That's the interesting thing. So here now the statement is an if then else statement. So now we need to use our rules for if then else. So we go to the rules. So for if then else, this is the rule we looked at just at the start of the lecture. So the postcondition from the if-then-else statement we put as postconditions for both branches of the statement, both for C1 and C2. And from that we need to reduce those to the precondition, the then precondition and the else precondition, which contain the precondition before the if-then-else statement together with the Boolean test of the if-then-else statement. In the then case it's true, in the else case it's false. Sorry, I want to go back to here. So this is automatic. This step we're going to, let's make the step. Right, so here we've added this statement here goes, we need to reach this at the end of the else branch of the if-then-else statement. And we get the else precondition, which is the precondition before the if-then-else statement we have here, which is xy greater than or equal to 0, the equality about the greatest common divisor, and x is not equal to y. So we then have that condition together with that the test, that's x is less than y, is false. So that gives us this statement. So at the end we have x is not equal to y, and so where I'm showing you the x is greater than y, this is really saying x is not equal to y. That's because that's in the precondition to the if-then-else statement here, and also x is greater than or equal to y, because that's what it means for the test x is less than y to be false. But if x is greater than or equal to y and it's not equal to y, that's the same as x being greater than y. So that's how we got this. Okay, so this is our else precondition, and in the same way in the then branch we need to get to the same postcondition here, the statement that we picked up from the end of the if-then-else statement, the postcondition to the whole if-then-else statement. And we also, at the end, we again have x is not equal to y, and we have the Boolean test is true, which is x is less than y. Since x is less than y implies that x is not equal to y, I didn't bother to write x is not equal to y also in here, because it doesn't add any information. Right, so now we need to justify this statement, and we've got an assignment statement above it, so this is automatic. We now just substitute x minus y for the variable x. So if we substitute x minus y for the variable x in here, we get that x minus y and y are greater than 0. If x minus y is greater than 0, that's saying that x is greater than y. So x minus y and y both being greater than 0 is the same as saying x is greater than y is greater than 0. And we also, substituting x minus y for x, we get that the greatest common divisor of x minus y and y must be the greatest common divisor of x0 and y0. That's just this equality with the substitution in. Now we need to justify this statement, and this is going to be implied by that. There's no program code in between, so it has to be implied, and fortunately this is a true implication. We'll look at that in a moment. So this is implied. If we go into this branch, we need to justify, it's pretty much the same. We need to justify the last statement in the branch. We've got an assignment above it, so now we assign, we now substitute y minus x for y. So again, so let's do that. So again, if x and y minus x are both greater than 0, that means that y is greater than x is greater than 0. And again, we're substituting y minus x for y here. So we get this statement about equalities of greatest common divisors. And once again, this is implied. And again, we'll look at that in a moment. And finally, we need to justify this statement just before the while loop. So that the greatest common divisor of x and y is the same as the greatest common divisor of x0 and y0, but that follows immediately from the precondition because x is x0 and y is y0, so that's an easy implication. And there we are, we've completed the proof of partial correctness, the partial correctness proof of Euclid's algorithm. So partial correctness, just to remind you, it means if Euclid's algorithm terminates, then it terminates with the right answer, with the greatest common divisor. we haven't proved termination, and I'd like you to have a little think if you can see a proof. Think for yourselves if you can see a proof of termination. Think about why does Euclid's algorithm terminate? And we had 3 implied rules here. Actually 4. Sorry, I should have mentioned the 4th. Anyway, so I've only mentioned the first 3 here. The first 3, I'll change this slide before I put it online. So the first 3 implications are these. The first one was trivial. That was if x is x0 and y is y0, then the greatest common divisor of x and y is the greatest common divisor of x0 and y0. The second and third are interesting statements. They're pretty much symmetric to each other. Well, they are symmetric to each other. So we'll just look at this one, the one in the middle. So this is saying that if we've got 2 numbers greater than 0 and x is less than y, then the greatest common divisor is essentially saying the greatest common divisor of x and y is the same as the greatest common divisor of x and y minus x. Because both these need to be the same number, which is the greatest. This is an assumption that x0 and y0 are such that it's the greatest common divisor of x0 and y0. So the important information here is that these 2 are the same number. Also that y is greater than x, but that's obvious, but that's already stated here. So there's a little lemma really about greatest common divisors here. Greatest common divisor of x and y when x is less than y is the same as the greatest common divisor of x and y minus x. So the point is, I mean, in this case it's not hard mathematics, but to verify these implications, in general, you need some mathematics. So this is a very simple, these 2 statements are very simple statements in number theory. Okay. So we've now looked at partial correctness in quite a lot of detail. I want to say a little bit, not too much, not too much in this part of the lecture, about what the mathematical properties of this proof system are. So when we looked at propositional and predicate logic earlier in the course, we had proof systems for those, and we had soundness and completeness results. Soundness saying that if we have a proof, we're really proving something that's true, and completeness saying if whenever we've got a statement that's logically valid, we can actually find a proof for it in the proof system. So do similar properties hold for Hoare logic? We've got a proof system, and certainly soundness is really important, because if soundness were false, then that would mean we could prove false statements, and we wouldn't want that. So fortunately, we do have a soundness theorem. And I've introduced notation so that the soundness theorem looks like it's the usual form of soundness theorem. We have a provability relation saying a Hoare triple, precondition phi followed by command C gives us postcondition psi. A Hoare triple is provable in using the proof rules for partial correctness if there exists a proof of it. And we'll say that a Hoare triple is true according to the rules for partial correctness if indeed it is true what we intend the Hoare triple to say. So that's saying for every state satisfying the precondition, if the execution of the command terminates, then it terminates in a state satisfying the postcondition psi. Okay, so this is the partial correctness assertion is true, the Hoare triple is true, and this is the partial correctness assertion is provable. And soundness, as usual, is that if a Hoare triple is provable, then it is true. So in this case, Soundness is proved by showing that each inference rule preserves partial correctness. And the most interesting case is proving that the partial while rule preserves correctness. So this lemma states the preservation of correctness. So if we look at the partial while rule, go back. Okay, I don't have this is the Tableau version. Never mind. So the premise of the partial, of course, the Tableau version is equivalent to the other version that's directly in the form of Hoare triples. The version in the form of Hoare triples makes it clear what we need to do to prove soundness, which is we assume that the premise of the rule is true, which is that the body of the while loop preserves the precondition preserves the invariant under the further assumption that before the executing state the test for the while loop is true, and then we need to show that the conclusion of the partial while rule is true under that assumption, and that is that if the invariant holds before executing the while loop, then it still holds at the end if the while loop terminates, and also if the while loop terminates, the test is then false. So on the slides, I give a kind of rigorous mathematical proof that of the soundness of the while loop, that is, that the statement in this lemma holds. But I do want to make sure, I don't want to go through this proof. This is written as a proof by formal induction. I want to essentially give you the same proof in a more illustrative form on the board instead, so that we can, just to make sure we understand why the partial while rule is sound. So we're going to show here the soundness of partial while. The partial while rule. Let's just put a bit more. Ooh, that's a bit big. So we suppose that the premise of the while rule is true. So that's that we have that if eta and b are true and we execute c, then eta remains true. I want to put the something else here, so let's write a small suppose. So because here I want to have that this is true, so I'm just going to write par like this, meaning this is true according to partial correctness. So we show, what we need to show is that the conclusion of the rule is true, so that is if we have a state satisfying the invariant eta and we execute while b do c, then if it terminates, then we still have eta and we have not b. And now, as I say, I want to show this in a kind of illustrative form so that we can see why it's true. So suppose S is a state satisfying eta. I'm going to use this notation for this. So eta is a property of states, and suppose S is a state that satisfies this property. So then we think about how we execute the program. So we're going to, So we're going to look at the execution of while B do C in state from state S. So we start off in a state S, and we have the property that S satisfies eta. Now there are two cases, two possibilities here. So either it's the case that in the state S, the test of the while loop is true. Actually, let's put that one on this side. Or it's the case that the test of the while loop is not true. So if the test of the while loop is not true, then the while loop immediately exits in the same state that we're in. The while loop doesn't go into its loop at all. So we terminate. So here we have while loop terminates, and we're in a state S where S satisfies eta, because we're still in the state S and S satisfies eta. So in this case, the test for the while loop B is the Boolean expression is true, then the while loop doesn't terminate immediately. We go and execute C at least once. So we execute C from S. And now we're proving partial correctness, so we only need to show that something holds if the execution of the while loop terminates. And if the execution of the while loop terminates, then every time we go round the loop inside, every time we execute the command C, of course that needs to terminate, otherwise the execution of the whole loop wouldn't terminate. So we can suppose this terminates in some state. So then we're in a state S prime, but by the assumption here that when we execute C from a state satisfying both eta and B, like the state S did, if we terminate, we end up in a state satisfying eta. So we get that we also have that S prime satisfies eta, because this is the state we get to at the end of executing C. So this is by assumption. And again, we're now in a situation we don't know if we've exited from the while loop yet or not, and we might exit right at this point, and we'll do this in the case that in the state S prime, which is the state we're not in, the test of the while loop is false. Otherwise, the test will be true. So in this case, the while loop terminates, and we're in a state S prime where S prime satisfies, where property eta is true. Let me write a neater eta. In this case, we go into the body of the while loop again. We go round the loop at least once more. So again, we execute C now from S prime. Again, we can suppose it terminates. Suppose terminates in state. Oops, let's write that more neatly as well. So again, we're in a state S double prime, and it's the case that S double prime still satisfies eta, again by assumption. And again, it might be the case that, so now, depending on whether our Boolean test B is true in the state S double prime, if it's false, then again, while loop terminates. In the state, now we're in the state S double prime because it terminates immediately, and still S double prime satisfies eta. Otherwise, we execute C from S double prime. And there's a whole infinite possible execution tree here. But if the while loop terminates, then it terminates after a finite number of steps, which means it can only terminate if at some point it goes down one of these left branches. So if some point the condition becomes false. And in each case where it terminates, we also have that the condition is false. So we see that if the while loop terminates, it terminates in a state. Let's call it D, satisfying eta and not B. And that's what we needed to prove, because we needed to show if it terminates, then we're in a state that satisfies eta and not B. So hopefully this picture helps you to understand why the proof rule for the while loop is correct. Let's go back to the slides. So on the slides, I've basically given the same proof, but I've wrapped it up rather than writing it pictorially. I've presented it as essentially a proof by induction on the number of iterations that the while loop goes through before it terminates. So you can read that for yourself. The important thing in the lecture was to explain to you why the while loop terminates. While the partial while loop is correct. And I wanted to do that in some detail because we're now going to look at another version of the proof for the while loop that is a bit more complicated. And this version is called the total while proof rule. And the total while proof rule allows us to prove total correctness. So with this rule, we're going to prove that we're going to prove that programs. We're going to prove total correctness statement saying that if a program satisfies its precondition, then it does terminate, and it terminates in a state satisfying the postcondition. So this is the relevant rule for the while loop. Right. So if we look at the blue part of the rule, or the blue and black, it's exactly the same as the partial while rule. So it's like the partial while rule, but we've just added some extra parts. And these extra parts are highlighted in red. And the extra part, so the blue part includes our invariant property eta, which, just as we had before, I used this terminology last week as well. So the property eta that is preserved by the body of the while loop and hence by the while loop as a whole, this is called the invariant for the while loop. But to show termination, we need something else which is called a variant. So whereas the invariant is a property, that's a formula in first order logic over our Boolean assertions, in predicate logic over Boolean assertions, the variant is an expression in the programming language, or in the logic equivalently. And this expression is called the variant, and it's called the variant because it's absolutely crucial that it changes. And the idea is that the value of the variant is guaranteed by the premise of the rule, so the statement on top of the rule, this guarantees that the value of the variant strictly decreases every time we execute the body of the while loop. It strictly decreases, but at the same time it remains greater than equal to 0. So if an integer it strictly decreases, if it's positive and it's non-negative and it strictly decreases, then and it stays non-negative, then it can only strictly decrease a finite number of times. And so the idea is, by constraining the variant, by showing that the variant satisfies this property, that it remains non-negative and we strictly decrease it every time we go around the body of the while loop. That means we can only go around the body of the while loop finitely many times. So to show that while B do C satisfies a Hoare triple, which is if the precondition eta holds, which needs to be an invariant, then when we run while B do C, it will terminate, we'll still have eta, and of course we'll have the negation of the test. To show that it will actually terminate, we need the additional precondition that we have such a variant E which is non-negative. And that variant needs to satisfy the property that as long as we start off with a non-negative variant before we, with the variant being non-negative before we execute the body C of the while loop, then the value of the variant in the state that we end up in here, the value of the variant will strictly decrease. So it's strictly below the value of the value it was originally before the loop. So here again, Z0 is one of these auxiliary or logical or ghost variables, so to speak, a variable not in the program. So I'm calling it a fresh variable here. That's just a variable that's not mentioned elsewhere in the statements that we've got. So as long as this needs to be a new variable, and then that means, well, of course, then this is guaranteed to have the value of E before we execute C, and so the expression, the variant E, is going to have a strictly smaller value because the variant of Z0 doesn't change when we execute C because Z0 is not mentioned in the program C. Okay, so that's the proof rule for total correctness. Here's the Tableau version, so it's basically just writing it out in the way that you would expect to. We want to prove a property of the while B do C. So our precondition for while B do C is again the invariant together now with the property saying the variant is non-negative. Our postcondition for while B do C is again is just as it was for the partial rule, the variant together with the negation of the condition. And to justify that this holds, we need to show that the inner body of the loop, that's the command C, preserves the invariant if it starts off in a state in which the test holds, and enjoys the property that the variant goes to a strictly smaller value but remains non-negative. Okay, so that's just the Tableau reformulation of this rule. And before giving an example of a proof using this, I want to argue that this rule is also sound. So we now have two new relations about Hoare triples. The first one says that a Hoare triple precondition command postcondition is true according to total correctness if it satisfies the total correctness property as introduced last week, which is the execution of the command C from any state satisfying the postcondition actually does terminate, and moreover it terminates in a state that satisfies the postcondition. And we want to show that our proof rules for total correctness are sound with respect to this notion of truth for a total correctness assertion. So here we've got the provability relation. This says the Hoare triple is provable using the proof rules for total correctness. So the proof rules for total correctness are exactly the same proof rules we had before. So the if then else rule, the assignment rule, the skip rule, the implied rule, but instead of the partial while rule, we have now the total while rule. So it's the same proof rules as before, except that we've changed the partial while rule for the total while rule. And once again, there's a lemma proved by induction in the notes that says if the premise of the total while loop holds, then the conclusion, the total correctness assertion in the conclusion also holds. So if the premise is true, then the conclusion is true. And that's the main lemma, and again that's proved rather technically by induction. So what I want to do again on the board is to give this argument pictorially so we can see how the rule actually works. So to save writing, let's copy the page that we've got, because I think we can do a copy and paste and then edit the page that we've got. So, oops, that was the wrong thing to do. So I need to select that page. So I need to copy that and then paste it. Right. Okay. So let's expand this. And let's put the new bits in red, just as they've been doing just as I've been doing on the slides. So we're going to have the soundness of the total, whoops, not totat, but total, of the total while rule. So the premise of the rule is still that C preserves the invariant if it starts off in a state that the invariant holds and the test for the while loop holds. But we also have that we have a variant now, which needs to be non-negative. So our E is non-negative, and we give ourselves a new variable z0 that the use of which is that we can refer to the value at the end of we can refer to this at the end of the in the post condition, and we want to show that C preserves the invariant and it reduces the variant. So at the end, so after executing C, we still have that E is non-negative, but it's now strictly less than Z0. So we're assuming that holds. Of course, we're supposing that this is because we're proving the soundness of the total rules for total correctness. We assume that this holds according to the proof rules for total correctness. Sorry, not the proof rules, but we assume that this Hoare triple is expresses a true property of total correctness, and we want to show that then as long as we start off in a state that satisfies the invariant and in which the variant is non-negative, as long as we start off in a state that satisfies the invariant and in which the variant is non-negative, then we do indeed terminate. Oops, let's keep this. And we do indeed terminate in a state that satisfies the invariant and the negation of the test. Okay, so now we suppose we're in a state that satisfies eta and that naught is less than equal to E. So then we can consider again, so the variant is, so we want to prove this total correctness assertion. So we suppose we're in a state that satisfies the precondition, and we want to show that the execution of while B do C does terminate, and moreover at the end we still satisfy the invariant and now the negation of the Boolean test. So again, we consider the execution of while B do C from the state S. We're in a state S satisfying eta, and we'll define, and we simply here define the value of Z0 at this point to be the value of E, which is greater than or equal to 0. So this precondition is satisfied here. So again, it's either the case that S satisfies not that the test is false, in which case, just as before, the while loop terminates, which is what we wanted to show, and indeed the resulting state satisfies the post condition for the while loop, so everything there is as before, or the test is true. If the test is true, we're in a state satisfying the invariant, this holds, and also the while and also the test is true. So now if we execute C from this state, well now because this is a total correctness assertion, we know that C does terminate. So we no longer need to suppose that C terminates. It now follows So now execution terminates. So this is by assumption. And the value of v. So this is all by the assumption. Let's rub that. And the value of e now, we have that 0. So the e is still non-negative because the assumption for the execution of C gives us that e is non-negative. And now the value of this is strictly less than Z0. So now we're going to define Z1 to be equal to the value of E. So we're going to again remember the value of E now in a new variable Z1. So all this is so this is all by assumption. And again, in this new state, S prime, well, either the Boolean test is false, in which case the while loop terminates, just as before, or the Boolean test is true. And now, if we execute C from S prime, then, of course, it doesn't matter that we called this variable Z1. I just want to distinguish it from the variable we had before. But because this, or rather it doesn't matter that we called it Z0, we could perfectly well call it Z1 up here. So because this property holds for Z0, where Z0 is a freshly named variable, it would hold whatever we called this variable. So in particular, if we look at Z1, the case of Z1, we have that now the precondition for the body of the while loop C holds. We've got 0 is less than or equal to E, and E is equal to Z1. So if we execute the body of the while loop, it again terminates, and again the value of E decreases. So again, here, execution terminates. In some state S prime, and again in this state S prime, we now have S double prime, we now have the invariant holds, and the value of E is still non-negative, but it's strictly less than the value we started with before executing C, which is strictly less than Z1. So now now 0 is less than or equal to E, is strictly less than Z1, and now we can define a new value Z2 to be equal to the new value of E. And we keep on with this argument. So we once again consider the whole tree of all possibilities. I want to say again, this is by assumption. So notice we're using the fact that we made our assumption was that a total correctness assertion holds to get that each time we execute C, the execution does terminate. And now we need to know that the while loop, the execution of the whole while loop terminates. Let's give myself a bigger tool for erasing. So we want to show that the execution of the whole while loop terminates. So if we zoom out, oops. Hang on, I thought I just rubbed that out. Well, let's rub it out again. So I want to zoom out a bit. So this is we're executing the while loop starting in state S. We might terminate immediately. If we don't, we certainly, at least the execution of C terminates of the first time round the loop, and then we might exit immediately, or we execute C again, which that terminates, but we still might not have finished going round the loop. So we again test to see if we exit the loop now, otherwise we execute C again, that's going to terminate, and so on. So each execution, every time we go around the loop, every time we execute the statement C in the loop, that execution of C terminates. But we want to know that nonetheless we can't go infinitely often around the while loop. So we still need, for the while loop to terminate, we still need to know that we can't go down this right-hand branch here forever. And the reason for that is that we start off with some value for E, which is in Z0, that is greater than equal to 0. And each time we go down, so let's put these in red. So here we have, let's put this in purple. So here we have 0 is less than equal to Z1 is less than E. And here we have 0 is less than equal to Z2. This is, oh no. Sorry. What I meant to say here is, here we've got the new variable Z1, which is less than Z0, the new value Z1. Here we've got the new value Z2, which is less than Z1, and so on. And each time we go down this branch, we start off with Z0, which is a non-negative integer. Each time we go down this branch, we find a strictly smaller non-negative integer. So Z0, Z1. So here we have 0 is less than equal to Z0. So here we've got Z1, we got Z2, and so on. And of course, we can't decrease non-negative integers, strictly decrease them infinitely often. So what we've got is execution cannot go forever down the right-hand branch as this would, execution cannot go forever down the right-hand branch, as this would lead to an infinite decreasing sequence of non-negative integers. So Z0 greater than Z1 greater than Z2 greater than So execution terminates. Okay. Good. So that's again, the pictorial proof. If we go to the slides, there's a more formal proof, again, proving by induction. So I won't go through that. The important thing is to understand the statement of correctness, and also why this proof rule for total correctness is formulated here, why it is correct. Right, so I just want to finish with an example finish this first half of the lecture with an example of a total correctness proof, and again we're going to use the Euclid's greatest common divisor algorithm. So what we want to verify is the same as before, but we're now going to do it using the Tableau rules for total correctness. So again, assuming that we start off with positive x and y, we want to show that the value of x at the end of executing the program is the greatest common divisor of the original values of x and y. So we need to, we had the while loop before. So before we implied the partial while rule, which led us to identify the identify the invariant, which is in blue here on the in the second assertion here. So this is the invariant again, that it's the same invariant as before, that x and y are positive, and the greatest common divisor of x and y is the same as the greatest common divisor of the original values x0 and y0. That's going to be the invariant. And the variant, we want a value that's going to be decreased, that's greater than or equal to 0, but is going to strictly decrease every time we go through the body of the while loop. And one such value, a simple one that decreases, is just the sum of the variables x and y. So that expression E here, this arithmetic expression x plus y, is our variant. Okay. So here before the loop, we just need to show that that's non-negative. In the do precondition, we give ourselves an auxiliary variable, z0, a new variable not mentioned in the program, that we set to be equal to the value of the variant. And at the end of the body of the while loop, we need to, the command that we execute inside the while loop, we need to show that that value has strictly decreased. So at this point, the variant is less than z0. So as with the partial while, when you're verifying a program, the clever things to do are to come up with the invariant, the property. Here we can use the same one before. And when you're showing a total correctness proof, you also need to come up with the correct variant. So in this case, x plus y is a correct variant. It's one possibility that leads to a simple proof. And this is basically all we need to do. We just need to check that the rest of the proof works with this variant in place. So again, here we're verifying an if-then-else. So we're going to duplicate this postcondition for the if-then-else, and it's going to be postconditions for both of the branches. So here we have that postcondition duplicated for both of the branches. And the precondition for each of the branches is again the precondition for the whole if-then-else, now together with, in the then case, the condition that the condition that the Boolean expression that the if is testing is true. So again, here we've got x is less than y, and here we've had x is greater than or equal to y, which combined with x is not equal to y is x is strictly greater than y, as before. And now we've got an assignment. So the assignment, we substitute x minus y for x. So as before, this gives us that x is strictly greater than y is greater than 0. We've substituted x minus y for x in here. But also, in the condition we were verifying for the variant, that 0 is less than or equal to x plus y is less than z0, we now substitute x minus y for x in here. So we've got x minus y plus y, we get x. So here we get the condition that 0 is less than or equal to x is strictly less than z0. And again, this is implied because, well, we already observed before that the blue parts imply each other. So here we check that also the red statement is implied. So here we've got the statement that 0 is less than or equal to x plus y, and that equals z0. But because x and y are both strictly greater than 0, then, well, y can't be 0, so x must indeed be strictly less than z0, as it says here. So exactly symmetric proof works for the then branch. So again, this is an assignment statement, so we substitute y minus x for y, which leads us to y is greater than x is greater than 0, y minus x in the greatest common divisor expression, and now x plus y, substituting y minus x for y gives us just y, and again, this is implied for the same reason as before, so this is indeed implied. And now all we need to do is verify the statement at the top, and again, this is an implication, and it follows for trivial reasons as before. We need to also verify that 0 is less than or equal to x plus y, but of course that's a trivial consequence from x and y being strictly greater than 0. Okay, so we've seen another example of a partial correctness proof. We've seen a proof of the soundness of the partial correctness proof rule for the while statement. We've seen the total correctness proof rule for while. We've seen a proof of the soundness of the total correctness proof rule, and we've seen an example proof of total correctness. I think that is more than enough for the first half of the lecture, so I'm going to pause the video now, and we shall resume again later with the second half of the lecture. Okay, bye for now.